Welcome. This is Physics for Caroline County High School, opening lecture on SI units, prefixes, dimensional analysis, and scientific notation. These notes are to accompany class discussions that have already occurred for this term. Our basic understanding of units will be challenged by the unusually large and small units that we'll experience in this physics class. As such, we will have to be able to convert between very large and very small using both SI system and scientific notation. In the SI system, we will have a base quantity with a unit name, and we will be able to put a prefix on that to come up with a derived unit that will be much larger or much smaller. To become familiar with the base units, we see here in the slide that length, mass, and time are our first concerns. The base unit for length, of course, is meter. For mass, it's the kilogram, and for time, it's the second. Also included is temperature, based on Kelvin, amount of substance, based on the mole, the electric current, based on the ampere, and luminous intensity, based on the candela. For example, in length, the meter can be subdivided into 100 smaller units, equal small units, the centimeter. It can be further divided to 1,000 small units, the millimeter. If we decided to go larger, we could have 1,000 meters, which we would refer to as the kilometer. The base unit for length, obviously, is meter. On the other hand, for mass, it's kilogram. We begin with 1,000 grams, and the kilogram is the base unit, mostly because of the utility of that measurement. The meter is a convenient length, and the kilogram is a convenient mass, much as the second is for time. We will become very familiar with these units and conversions of the units as we go. The derived units that I mentioned before are a combination of the base and a prefix. We will also see where we will have derived units such as area, which is length times length, volume, area times length, density, mass per unit volume, speed is a distance per unit time, and acceleration is the change in speed per unit time. Force is mass times acceleration, pressure is force per unit area, and energy is force times distance. These units are derived units. We must be very careful when working with units that when we multiply them, they are of the same base. They must have agreeing terms. We cannot multiply kilograms and grams. We must have the same unit for both. On the other hand, we can multiply kilograms times cubic meters, for instance, to get density. If they are not of the same quantity or quality, that is, then they can be multiplied using different base units. We'll see this in more examples as we go. The prefixes for the units are very important. As we know, the meter is about 3 feet, would be a conversion for something that we were very familiar with. If we had 1,000 meters, we would call that a kilometer. This is also something we are somewhat familiar with. We could also speak about 1 billion kilometers or 1 billion meters as in a gigameter. Notice the utility of these prefixes. We can suddenly go from discussing something that is very small to something that is tremendously large, from the atomic scale to the universal scale, simply by changing the prefix in front of the word meter. If we speak of something as being a picometer, it is a meter divided into trillion. On the other hand, if we speak of a gigameter, it is a billion meters. The utility of going from one to the other by simply changing the prefix is uncomparable. It is the way that we will use to speak of very small and very large terms. Some conversions that you might try on your own: you would want to start with the unit you are solving for. What you want is written in the numerator, and the unit you are starting with, what you have, is written in the denominator. So, as we have seen in the factor label method, we would write our cross. This is most easily demonstrated during class time. What we always want to remember that the larger unit will get the smaller number, usually 1, and the smaller unit will get the larger number, the prefix meaning. 1 meter is the larger unit, and 100 centimeters is the smaller unit. You must know your prefixes and what they represent. I would refer you to table 2.2 on page 18 of the text. So if you would try to convert 36 centimeters to meters, and a second example that you could attempt is 0.746 centimeters to kilometers. If you would like, you can pause now and perform those. After you are done, we'll move on. The next big step is to become proficient with scientific notation. It expresses numbers as multiples of two factors: a number or a coefficient greater than or equal to 1 but less than 10, and then 10 raised to a power. 4.18 times 10 to the 8 would actually be expanded to include 4, 1, 8, and 6 zeros. If the number is to be expressed in scientific notation is greater than 1, the exponent is positive. However, if it is less than 1, the exponent is negative. Greater than 1 is a very large number or a large number, and less than 1 is a decimal. 0.00008 would be 8.0 times 10 to the 4th. The exponent tells you how many places the decimal has or is to be moved. For example, 418 would be 4.18 times 10 to the 2, or 8.69 times 10 to the negative 3 would be expanded to 0.008619. We will see the utility of scientific notation in the significant digits. We will need to know about the quality of the significant digits in scientific notation. More on that later. That concludes the presentation on scientific notation and derived units. We will revisit these frequently in our studies during class time. Thank you.